Hi everyone, it's Dr. Harbison. So we're going to try to answer a question about stellar properties today, which is what is the mass of our stars? Now we could assume that a star like our sun, which we know the mass of because it has planets, we watch them orbit, we use Newton's laws, we figure it out. We know the mass of our sun is one solar mass, which is about 2 times 10 to the 30 kilograms. Our sun is quite massive in terms of everything else in the solar system. And we could assume, well, if we find more main sequence G-type stars, they're probably about the mass of the sun. But, what about an M-type star? What about A or O? What about those red giants and white dwarfs? What are their masses? And how we can figure this out is we need to find some places where we can use gravity. Let gravity work and do the same thing that we did with the sun. And until recently, within the last few decades, we haven't found any planets around other stars, we're going to have to use other stars. So that's where binary stars come in. Okay, so what we're going to do is look at binary stars, and we're going to look at a certain type in particular called eclipsing binary stars. And we're going to look at what these tell us about stars. So our sun is a single star. It's one star and a bunch of planets. But many stars in the universe are binaries or trinaries or otherwise multiple star systems. They have many stars orbiting each other. So for instance, this is a picture of the southern sky, the constellation Centaurus and the constellation Crux. The star pointed out is Alpha Centauri. It is our nearest neighbor, and it is a triple star. What the arrow is pointing at is actually 2 stars. They're just really close together compared to how far away they are. So they look like one. And then there's a little red dwarf, Proxima Centauri, hanging off, too faint to be seen in this picture. So these 3 stars orbit one another. Now, how do we know about this? Well, some stars are close enough to Earth or they're far enough apart that we can photograph them. That when we point a telescope at these stars, this is, I believe, Albireo, Beta Cygnus, we see 2 stars, even though with our eyes, without a telescope, we only see one. You can see many systems. For instance, there's a star called Epsilon Lyrae that's a famous system called the double-double. It's 4 stars and kind of 2 sets of 2. But we don't just need to identify, oh, these are binary stars. We need to see them orbit. We need to know how far apart they are, what is their average distance, and what is their orbital period. Those are the 2 things we need to know. There's kind of a sweet spot where we can watch 2 stars orbit. They need to be close enough to one another that their orbital period, which remember Kepler's laws, the closer 2 objects are to one another, the shorter their orbital period. So these stars need to be close enough to each other that the orbital period isn't like thousands or hundreds of thousands of years. We won't be able to see that. But they need to be well enough separated that we can tell, yep, there's 2 stars there. We can actually see star A, star B, not just a little blob that makes up both of them. And because, what we care about here is the angular distance, how far apart do the 2 stars look from Earth rather than the actual distance, how far apart the 2 stars are. At least when we're trying to say, do we see 1 star or 2 stars? We tend to do this with nearby stars. Alpha Centauri, we can literally see A and B orbit each other. Proxima Centauri is harder because it's much farther away than A and B are from one another, so it's orbiting very slowly. And here's another example. This is a brown dwarf system. Again, like many brown dwarfs, it doesn't have a very pretty name. And on the bottom, you can see there's a bunch of pictures of this system. If you assume the brighter one is fixed in place, you can see that the fainter one is circling it, and then the little picture in the center shows what we actually end up working on. This is how we know the mass of these brown dwarfs. Is we could measure how long it's going to take for these to orbit. Looks like they've got maybe 1/3 to 1/2 of their orbit done in about 4 or 5 years. So we can calculate that. We can then use the fact these are nearby stars. We can get their parallax to figure out how big this orbit physically is after we measure how big it looks on our sky. And then, you know, we have the masses. And we can even do this without seeing both stars. So here's some interesting facts. Sirius is the brightest star in the sky. Or rather, Sirius A is. It's a nice A main sequence type star. It's really bright. But remember, it's got a companion. It's got the closest known white dwarf, Sirius B, orbiting it. And white dwarfs are very faint. That's why they live at the bottom of the main sequence. So what astronomers noticed in the 1800s was Sirius A was moving across the sky. It's relatively nearby, so even if you watch it for decades and decades, you can see a slight motion as it and the sun both move around in the galaxy. So Sirius A is doing that. We'd expect it moves in a straight line or nearabouts, but it didn't. It kind of bobbed back and forth. So what it kind of looks like is you're watching a mime who's acting like they're holding something really heavy, but since they're a mime, you know, they're not really holding something, they're acting. But you can see them move in response to the really heavy thing, and you're like, oh, they are holding something really heavy. Sirius A was moving in response to something relatively heavy moving with it. That heavy thing was later found to be Sirius B. So this picture shows a diagram of what Sirius A's motion looks like. And then in a yellow line, and then the Sirius B's motion is in an orange line. And if you track kind of their average position, together they move in a straight line. This is an idea physicists call a center of mass. And we're going to talk more about this with with discovering extrasolar planets. We want a kind of close-up model. What we're going to do is pull out one of the NAP labs. This is the eclipsing binary lab, but we're going to ignore the eclipsing part. So here we have two stars. Let's make one of them kind of Sirius A-like. Looks about right, and one of them will be our Sirius B. It's a little tiny, very hot star. There we go. Now, what happens here is because these two stars are relatively, that's a bit big for Sirius B. Let me fix that. So because these two stars are relatively comparable in mass, they're both stars, we could draw what the small one orbiting the big one, or the big one orbiting the small one, but what's actually happening is they're both orbiting what's called the center of mass, their average mass. Now, since Sirius A is more massive, that's why it's called Sirius A, it's moving in a smaller circle around it. Because Sirius B is less massive, and I've zoomed this in a lot because I wanted a system that was going to orbit nice and fast rather than slowly. But because Sirius B was less massive, it's making a wider thing. It's like a seesaw. If you want to balance a seesaw and you have two people of very different masses, the heavier person has to sit much closer to the center pivot. So there's our center pivot. So the center pivot is the green X, which is mostly covered by Sirius A. Then Sirius A is our heavy person, and then Sirius B is like our little light toddler. All right, so that is a key thing about binary stars. That's what we're seeing here. And we're going to come back to that more with planets. We have some stars that we can see as binaries. We call them visual binaries. They're because we see them. But some stars are too close and too close to each other and too far away from Earth to see them as separate stars. Now the question is, how might we tell that they're two different stars? Now, if you have two stars that are really different, an A star and an M star, when you look at their light with a spectrometer, you're going to see two sets of spectral lines. You'll see the ones you expect for the A star and the ones you expect for the M star kind of on top of one another. But there's another thing we can notice about close-in stars, or at least a few of them, and that's that some of them are lined up really precisely. So stars orbit each other at no particular angle relative to the Earth. Each star system has its own kind of preferred equator plane. So there's no reason that all star systems will orbit in the same direction and at the same angle as the sun and the planets. So if by coincidence, some of these star systems that orbit each other are edge on from our point of view. So what they're doing is they are orbiting like that. You can look at me in the picture. Actually, I'm going to stop screen sharing. So some stars are orbiting face on. They're orbiting like this. You can, when you look at them in the plane of the sky, you can see them basically, the two stars literally circling one another. But some systems are orbiting kind of tilted. They're orbiting like this. So they're partially moving towards and away from you, or from, and by you I mean Earth, but partially you could still see them making kind of a circle. And some of them are orbiting edge on. So they're orbiting like this. So most of what we see is them moving towards us or away from us. Yeah. So, and remember, we can detect that. We can detect that with radial velocity. But there's another thing that if they're moving towards or away from us, that happens, and that's that sometimes when one star crosses in front of the other star, and we have what's called an eclipse. You know, we remember that eclipses happen with the moon and the sun, and you can have them with any two bodies, in this case, two stars. So we call these eclipsing binaries, and they're really easy to spot. And they can be really easy to spot because every orbit, we're blocking one star or another, so the combined light of the stars gets dimmer. In fact, the most famous one is called Algol. It is a star in the constellation Perseus. If you know the story of Perseus, he was a Greek hero, and one of his major deeds was killing Medusa the Gorgon. And she was transformed into a monster, her gaze petrified things. And when the Greeks imagined Perseus the constellation, they put Medusa's severed head as the star Algol because they noticed occasionally it would suddenly get fainter. The Arabic astronomers were the ones who actually named it. Algol comes from Al-Ghul, the demon. It was the demon star because it wasn't nicely behaved. It didn't shine constantly. It suddenly flickered, and they found it kind of ominous. Now, what is actually going on with Algol is it is not one star. It is two stars, and occasionally one of the stars covers the other. In fact, so the dimming they were seeing was just one star in front of the other blocking some of the light. So the top is what we'd see if we were close to Algol, if we were close enough that we could tell that there were two stars. The bottom is what we call a light curve. A light curve is basically just measuring how bright a star is with respect to time. We're just graphing how bright is this thing. Now, most of the time, we're seeing the brightness of both stars. Remember, we're far enough away from them that we can't pick out the individual stars. We're just seeing they're basically sitting on top of each other from our telescope's point of view. So we see both A and B's brightness. But we have two special times in the orbit. One is when B is in front of A, and one is when A is in front of B. So when B is in front of A, B is a smaller star. So what happens is it covers some but not all of A. So we get a dip. Sometime later, A will be in front of B. Since A is the bigger star, it'll block all of B's light, so we get another dip. So we call the bigger dip the primary eclipse, and the other eclipse is the secondary eclipse. Now, here's an interesting thing. What matters here is not actually the star's sizes. It's their surface temperatures. So let's go back to our animation. All right, so let's try to simulate Algol. I've set up a blue star and a red star. Red star is big, the blue star is small. Now I'm going to click us on to Earth perspective. So this is what Earth sees. Occasionally we see the red star and the blue star. They're the blues in front of the red. They're the reds in front of the blue. Now, if we look at our light curve over here, when the blue star is in front, we get a little dip. Small blue star in front, we get a little dip. Big red star, we get a big dip. Now what I'm going to do is switch the temperatures of these two stars. So this one's about 5,000 versus 8,000. So I want you to watch what happens. Okay, that's roughly the same. Now, the big blue star in front makes a little eclipse. Big red star, or small red star in front makes a big eclipse. So the thing that's in common with those two things is that when the cooler star is in front, we get a bigger eclipse. When brighter star is in front, we get the little eclipse. It doesn't actually depend, while the details depend on the size, which one is bigger only depends on which star is hotter. So that's the important thing. We can tell which one star is supposed to be in front by which one's the bigger eclipse. A bigger eclipse means the cool star is in front, the red star is in front. A small eclipse means the blue star is in front, regardless of their size. Now we can also, now here's the thing, with eclipsing binaries and visual binaries that we can see orbit each other, we can use Newton's laws to get their masses. For the eclipsing binary, what we know is we know how fast they're orbiting because we can, or how long it takes them to orbit because we measure their time. We measure their periods, we measure how often we see eclipses. And we can tease out how big the orbit is based on the size of the stars. We can measure, you know, the bigger the star, the bigger the stars involved, the longer the eclipse is. So we can test out, you know, how big these stars should be, compare it to our models of stars as black bodies, where if we know their luminosities and temperatures, we know their sizes. We can also then get their masses. And we can also look a little bit at age, but I'm going to talk more about that later. In sequence, we notice a trend, which is that the cool stars are least massive and the hot stars are the most massive. So the main sequence is sorting by mass. The thing that makes all these stars are turning hydrogen to helium, but the reason they're not all at one spot is because they all have different masses. And this kind of makes sense to us. We know that from the sun, if you increase the temperature and pressure in the core, you know, and the pressure is basically because you are piling on more stuff, the fusion rate goes up. So stars are producing more energy. So we'd expect it to be more luminous, which would put them higher on the main sequence. Now, this also makes predictions about star lifetimes. You know, remember the star's fuel is set by how much mass it has. How fast the star is going through the fuel, we can measure based on how bright it is. And we do the math, and we discover that even though big stars have more fuel, they go through it far, far faster than a little star. So they tend to live much shorter lives for stars. If you see the numbers on this plot, you know, the smallest number for age is 10 million years. So, you know, stars still, even a big star lives a pretty long life compared to a person. Big stars are kind of the tractor trailers of the star world, while little stars are kind of the Priuses in the compact cars of the star world. You know, that little star has a lot smaller gas tank, but it's a lot more fuel efficient. All right, so in summary, we have a number of binary stars. One of the interesting kinds are eclipsing binary stars because we can measure not only the size of the two stars, but the size of the orbit and the period of the orbit, which will give their masses. Now the rule is the hot star is blocked during the primary eclipse, the cool star is blocked during the secondary eclipse, regardless of star size. And what these binary stars let us do is they let us see trends, like on the main sequence, how does mass correlate with spectral type? Now that's only true in the main sequence. Once we have a red giant or a white dwarf or a supergiant, some other things are going on. So we're going to take a digression for a bit, because we can not only use gravity to look at stars and study stars, but we can use it to find planets. We talked about how we used Sirius A being wobbling back and forth by an unseen mass to find Sirius B. Turns out that works reasonably well with much smaller masses. So we're going to go looking for some planets.